Welcome to Power Electronics Education Electronic Book, Lecture 3, Diode Rectifiers. This lecture is presented by Dr. FIRUZ ZARE. Now let's start with the resistive load. That means we have bridge rectifier, which is full wave diode rectifier consisting 4 diodes. Then we can see how the circuit works. Let's consider first half a cycle when the input voltage is positive. That means we have positive voltage across this terminal. So starting at this zero crossing point, the current through the resistor is 0. That means the output voltage is 0. So once we have positive voltage here, so here we can see that we have positive voltage across this diode and positive voltage across this diode. That means for the first half a cycle, D1 and D4 conduct, and this is the circuit diagram. D1 resistor and D4. So if the input voltage is positive, here you can see that we have positive voltage across this diode and positive voltage across this diode. So in this case, D1 and D4, they can conduct, and that's why suppose that the voltage across the diode is 0 when the diode actually conducts, then input voltage appears across the load. So in the second half a cycle, when the input voltage is getting negative, that means from this time, which is t/2, till this time, so the input voltage is negative. So we can say that this is the polarity of the input voltage. Now, because we have negative voltage across D1 and D4, they are off. And if you look at the polarity, so cathode is negative, here anode is positive. So in this case, D3 and D2, they conduct. And that's the circuit diagram again. Input voltage, this diode D2, back to the resistor, and then back to the diode D3, and then come down through the power supply. So because this is negative, for the second half a cycle voltage is negative, so here we can see that we have negative across this diode, which is basically we can have forward bias. And also here, if you look at this terminal is positive, that means this terminal is positive, then we can have forward voltage across this diode. So D3 and D2, they can conduct. If they conduct, you can see that here positive voltage appears across through this line across the load. So again, for the second half a cycle, we have positive voltage. That means if you look at this circuit again, when this diode conducts, D3 and D2, they conduct, we can see that we have positive voltage. So that's why for the second half a cycle, again we can see that we have positive voltage. So this is the output voltage waveform. And if we have resistive load, current is voltage divided by resistor. So that's why the current waveform is similar to voltage waveform. In this circuit diagram, we have almost same full wave diode rectifier, but we have different load. We have pure inductive load. As I mentioned before, we can consider that one as a current source. That means if you have a large inductor and if the current through the inductor is continuous, then we can consider that one as a current source. So what's happened? When D1 and D4 they conduct, so in this case we have current through D1 and this is load current which is constant. So in this case we can see that we have positive current, so input current here is shown here. That's input current. So basically input current is same as output current for the first half a cycle, but for the second half a cycle, because we turn on D3 and D2, still load current same, but the direction of input current is changed. For example, when D3 and D2 conduct, that means this is the direction of current flow through D3 load back to the D2, and now this is the direction of current. So now this is the direction of current. So for the second half a cycle, current is negative. So if you look at power system grid voltage, and suppose that we connect one diode rectifier with a large inductor, which means current source. So the current that we inject into the system, into the power system, is not a sine wave, is a square wave. So this current consists of sine wave plus harmonics. That means we inject significant harmonics into the power system. According to IEC standard, we are not allowed to increase and inject harmonics into the power system. We need to actually control that one. So basically in high power diode rectifier, when we have significant or large inductor, that means we may disturb and inject harmonic into the system, and we have to control that one either using active or passive filter. We can find the output voltage of the full wave diode rectifier. This is the equation. Basically for the first half a cycle and the second half a cycle we have same equation. Again, the DC voltage is this defined integral. This is the lower limit of integration, upper limit of integration. And again we can split into two parts. We have same voltage for these two parts, except the limits of integral different, but we can simplify into this equation. That means 2 times of this equation, and the reason is that this area is almost same as this area. So in order to calculate this integral, we can calculate this integral and multiply by a factor of 2. So this equation means the defined integral of this area, and because we have found this integral for the half wave diode rectifier, then this is the output voltage for a full wave diode rectifier. That means if the input voltage is Vm sinus 2 pi T over T, the average DC voltage is 2 Vm over pi. In some applications, when we are talking about, for example, DC voltage, that means we need to have a DC voltage with less ripple. So the output voltage that we got from the previous diode rectifier are either full wave or half wave. So these type of waveforms are not suitable for several applications. For example, if we have electronic device, we need to have good DC voltage with less ripple. So that's why we need to have a filter. This is a very common type of diode rectifier with capacitive and resistive load. That means when we have full wave diode rectifier, this is basically the output voltage without capacitor. So this is the red voltage waveform is the output voltage with only resistive load without any capacitor, but the blue one is based on resistive and capacitive load both. So initially when the voltage across the capacitor is 0, that is fully discharged, when we apply voltage, so we have inrush current. So this is quite important. When you design a rectifier, you have to notice that if this inrush current is significant, you may damage the power diodes. So that's why you have to consider that inrush current in some power electronic circuits, especially high power system. We need to control this inrush current. So this is one of the issues that I would like to highlight in this application. The second is that this ripple, you can see that this voltage is much better than this voltage waveform, but still we have ripple. So the point is that by changing the filter we may have a better output voltage, but another problem is that the line current, input current, is not sine wave. This is the current. So again, if we have high power rectifier connected to the grid and the current taken from the grid is basically not a sine wave. So rectifier connected to a capacitive load and a resistor shown here means that we have a sine wave, because in frequency domain here we get sine wave plus harmonics. That means this voltage, this current waveform consists of sine wave plus harmonics, and we inject significant harmonics into the power grid, power system. So that's why we have to notice, we have to consider, we have to find if there is a significant harmonics injected into the system. We need to control that one using passive or active filter. Now let's look at the battery charger with the full wave diode rectifier, and when we have an inductor at the input side, this inductor can limit the current. So the point is that once the input voltage is greater than battery's voltage, this diode and this diode can conduct. Then we have current through the diode and through the inductor, and then we can charge the battery through this loop, through this current loop. So basically this is the current pass through the diodes D1 and D4, and again at this instant of time, because the current through the diodes are 0, then we turn off the diode and we cannot turn on them until next cycle. So for the second half a cycle, when the input voltage is getting negative, and at that voltage level we can turn on this diode D2 and D3, and then we can charge the battery through these diodes. The point is that if you look at this terminal, this is the voltage across this terminal, and that voltage has been affected by this load and also line impedance. So that means if we have a device connected to this terminal, the voltage across this device is not sine wave, it's basically that voltage level. So we don't have sine wave across this device. That means when we have high power battery charger, and if we don't have a good filter connected to the system, we may disturb other electronic devices. This is another battery charger in which the inductor actually placed at the output side with same diode rectifier. So here we can see that we can charge the battery through the inductor and diodes for the first and second half a cycle, but the point is that the input voltage is almost sine wave. That means if we have another device connected to this terminal, the voltage across the device is sine wave because this device actually get this voltage waveform. So here we can see that when we have a filter on the output side, and if we have less line impedance, we may get better voltage waveform and affects less other electronic device. Now let's look at another battery charger in which we have two inductors. One is placed at the input side, the other one at the output side, with the same diode rectifier, full wave diode rectifier. So here we can see that the voltage at this terminal is not sine wave, but at least better than the previous case when we had only an inductor here. And that shows that still we can charge the battery for the first half a cycle and the second half a cycle. But if we have another device which is basically connected to this terminal, the voltage waveform is not pure sine wave. So that means in real case, if there is a generator and if you have line impedance, then if we have a rectifier connected to this power grid, either with the battery charger or current source, that means we need to consider the effect of line impedance on this voltage, especially when we have high power diode rectifier. So this issue will be investigated at the end of this lecture. Why we need doubling output voltage? Some appliances like computer may operate in two different countries in which grid voltage may be 110 volts or 220 volts. So instead of designing two different power supply, we may have single power supply with the special switch in which you can change the position of switch, and then the system can operate either at 110 volts or 220 volts. This is basically two half-wave diode rectifier, and then we can get more voltage across the load based on this simple circuit diagram, which consists of two capacitors in series. Let's start with the first capacitor, starting from initial condition. That means the voltage across these capacitors are 0. For the first half a cycle, because the voltage across the capacitor is 0, suppose that the input voltage is positive for the first half a cycle, then this diode conducts. We have input voltage across this capacitor. So that's why for the first half a cycle, the voltage across this capacitor is same as input voltage. At this time, because the voltage across the capacitor is the maximum voltage that comes from the input, so after this time, because the input voltage is decreasing, so this diode is turned off because the voltage across the diode is negative. So this capacitor can provide power for that resistor until next cycle. So let's look at the second capacitor. So for the second half a cycle, when the input voltage is getting negative, in this case we have negative voltage here, and as I mentioned before, initial condition is 0. That means the voltage across this capacitor is 0. So when we have negative voltage, this cathode is negative, this terminal is positive. That's why we have that voltage across this capacitor. So again, the voltage across this capacitor is increased until this time, and because the input voltage is decreasing, but still the voltage across the capacitor is greater than input voltage, so that's why this diode is turned off, and that capacitor can provide enough voltage and power for the resistor. So here we can see that we have two capacitors with this polarity, and this resistor see these two capacitors in series as a voltage source. So the voltage across this resistor is the sum of this voltage and this voltage. So that's why the output voltage is double. How we can change this circuit with doubling output voltage to a normal circuit? So basically, if we compare this full wave diode rectifier with this doubling output voltage, here we can see that the input terminal is connected to these points, so we can define same terminal. So we have almost same diodes connected in series in this leg, which is almost same as this diode through this leg. So a difference between this circuit diagram and this circuit diagram is that we need to have two diodes plus one switch. So if I add one diode in this circuit diagram and another diode in this circuit diagram, and then disconnect this part and put the switch here, so in this case this circuit diagram can operate either in normal mode or doubling mode. That means if the switch is off, this is normal operation. If the switch is on, then this is doubling. That means if we need to have, for example, DC voltage around, for example, 300 volts, if the line voltage is, for example, Vin, which is equal to 150 sinus omega t, then we can have doubling circuit. So in this case we get approximately that voltage if we have a large capacitor with less ripple. And in another circuit, if we connect to another grid with this voltage, 300 sinus omega t, omega is basically 2 pi over t. So in this case we need to switch off. When we switch off, we almost get 300 volts. But the difference is that this circuit needs two capacitors, while in a normal circuit with diode rectifier we may have one capacitor connected to this terminal. Another point is that ripple may be significant, because in half-wave diode rectifier when we have this type of voltage waveform, we get that voltage from first capacitor and the other one from second capacitor. So this ripple may be significant. How to improve this ripple? How to reduce this ripple? We can reduce this ripple by large capacitor, which increase the cost of system. So that's why this circuit may be suitable for low power system, in which we can get that voltage level and then we can regulate that one using another DC-DC converter. Let's start multi-phase diode rectifier with star connection and resistive load. So this is a circuit diagram which consists of 6 phases, and here we can see how the input voltage is rectified. Let's start with phase 1. Basically, here we have 6 diodes connected in this configuration, and the load actually is connected between this terminal, ground, and this common point. So because phase 1 is greater than other phases, that means this voltage comes from phase 1 and the voltage across these diodes are negative, and the reason is that V1 is greater than V2, V3 and till V6. So in this case the only diode which conducts is D1. So over this cycle, over this time, the input voltage appears across load and the rest of diodes are turned off. So same scenario happens for phase 2, phase 3 and others. That means in the second cycle we may turn off D1 and then turn on D2. Now let's look at the second interval. In this case V2 is greater than V1, V3, 4, 5 and 6. So that's why this voltage is basically connected to, this terminal is connected to V2. D2 is conducting, so that's why the voltage across these diodes are negative. So what's the output voltage? Basically output voltage is this portion of phase 2, and output voltage for this interval is portion of V1. So V1 and then portion of V2, and same things happen for another phase. That means over this cycle, because V3 is greater than other phases, so here we have V3. So same for other phases, for example V4, V5 and V6. So here we can see that over one cycle, that means if this is a sine wave, over one cycle what we get 6 pulses together, which actually provides voltage for this resistive load. And what's the DC voltage? We need to find this area over this cycle, this interval, or whole area over that cycle. So that's another way that we can measure and find the output.